Module 613, the Fletcher-Munson Equal Loudness Contours, Fons, and SPL Weighting Scales. Back in the 1930s, Harvey Fletcher and Wildon Munson, two researchers at Bell Laboratories, the company responsible for providing telephone service in the U.S. at that time, did some research to find information about how we perceive volume. They had people come into a quiet room and listen to pairs of tones at various frequencies and dB levels. The listeners were asked to say whether the first tone was louder or softer than a second tone. Then they took these results and created a graph that shows how we perceive sound at different frequencies. The graph is shown here. These curves are the infamous Fletcher-Munson curves, otherwise known as equal loudness contours. Loudness is the term that we will use to describe the perceived volume of sound. The unit of loudness is called a fon. Each line on the curve represents equal loudness, 10 fons, 20 fons, etc. The x-axis shows frequency, and the y-axis shows dB SPL. Before I explain how to read this graph, let's talk about frequency response. Frequency response refers to how a system, for example a car radio, headphones, a microphone, a guitar pickup, or your hearing, responds in amplitude at different frequencies. Let's use an iPhone as an example. Internally, the electronics of an iPhone have what we call a flat frequency response. That is, the curve is a flat line, and it doesn't reduce or amplify any frequency more than any other. This is usually a good thing. However, when you play music through an iPhone speaker, it does not produce very much in the way of bass or low-frequency sound. You would probably refer to the sound as thin or tinny. The frequency response graph of an iPhone speaker looks like this. Almost no amplitude at low frequencies, and a medium amount at higher frequencies. Now, if you listen to an iPhone with a good set of earbuds, or even better yet, headphones, you should hear a lot of bass. Here is the frequency response graph of the headphones we have in the lab. As you can see, it is a lot closer to flat than the iPhone speaker and produces more low and high frequencies. If you are used to looking at a typical frequency response graph, the Fletcher-Munson curves will be a bit confusing. This is because the graph shows the SPL needed to hear rather than what the ear is hearing. What this means is that the graph will appear to be upside down compared to a regular frequency response graph. So, if you have trouble wrapping your head around the graph, just mentally flip it upside down and it will make more sense. And now to explain how to read the graph. Let's look at the 50 fon line. At 1000 Hertz, it crosses the 50 dB line. That means a 50 dB 1000 Hertz tone will have a loudness of 50 fons. Now, let's follow the 50 dB line over to 4000 Hertz. That point is between the 50 and 60 fon line at about 57 fons. That means a 50 dB 4000 Hertz tone will sound 7 fons louder than a 50 dB 1000 Hertz tone. Notice that all the curves have a similar dip around 4000 Hertz. That indicates that it takes less dB at 4000 Hertz for us to perceive a sound as being the same loudness as a 1000 Hertz tone. Let's stay on the 50 dB line and move over to 50 Hertz. That point is between the 10 and 20 fon line at about 14 fons. That means a 50 dB 50 Hertz tone has a loudness of only 14 fons. That is very soft. Notice that all the curves turn up at lower frequencies. That means that our ears are much less sensitive to lower frequencies. it would require the 50 Hz tone to be played at 72 dB to sound the same as the 50 dB 1000 Hz tone. This graph shows that the ear's frequency response is not linear and that it is more sensitive to frequencies around 4000 Hz. Let's see why that might be. The average ear canal is about 2.2 centimeters long. If you remember, it acts like a tube closed at one end, and the resonant frequency would then be F equals V over 4L. So, plugging in numbers, we get 343 meters per second divided by 4 times 0.022 meters equals 3,898 Hertz. So this is a good explanation for the dip in the Fletcher-Munson curves at 4,000 Hertz. These curves also show that the ear is less sensitive to frequencies below 500 Hertz, and that the softer a sound gets, the less linear the frequency response is. This also explains why the sound on your car radio or music player sounds thinner, lacking low frequencies, when you turn down the volume. It's because the ear is less sensitive to low-level, low-frequency sounds. This has important ramifications for audio engineers when considering monitor levels. Turning down the volume on your monitors will cause you to think that your mix is deficient in bass or low frequencies. So, if you mix at too soft a volume level, it will sound very bass-heavy at normal or loud listening levels. Two more things to take note of. Fons are referenced to our hearing at 1000 Hz, so at 1000 Hz, the value in fons equals dB/SPL. Remember that all sounds on an equal loudness curve will have the same loudness. Sound weighting scales. Because we are less sensitive to low frequencies than high frequencies, when taking sound level measurements, we sometimes want to take into account how the sound level is perceived rather than what it actually is. So we have A, B, and C weighting curves that we use in sound level meters that roll off the low frequencies so that the measurements will match our hearing. There are two weighted scales that are commonly used. The A weighted scale is based on a 40 fon curve. This de-emphasizes low frequencies below 500 Hz. This is the most commonly used scale for measuring sound levels, as it corresponds to how we hear at moderate sound levels. The C-weighted curve is based on the 100 fon curve. It is mostly flat and generally corresponds to the actual dB/SPL that is occurring. The B-weighted curve is based on the 70 fon curve, but it is rarely used. To review, loudness is the perceived volume of sound. The unit of loudness is called the fon. At 1000 Hz, fons equal dB/SPL. Human hearing is not sensitive to low frequencies, especially at lower SPLs. Human hearing is very sensitive to frequencies around 4000 Hz. The A-weighted scale is used for SPL measurements that correspond to the way we hear by reducing its response to low frequencies. The C-weighted scale has a mostly flat frequency response and essentially shows what the actual SPL is.